All right, so okay, welcome to class today. I can you all see? Is it broadcasting down there? Awesome. So I have a PowerPoint, but during the PowerPoint, I'm gonna do some I'm gonna do some demonstrations using this data set right here. It's called. There is another link to some other data that you'll use in the lab. Um, and but this is the data that I'm going to demonstrate in the class. So you can, if you want, you can follow along, but you don't have to. It'll be recorded. But that's I am giving you a copy of the data. That's what I'm trying to say. I'm going to go ahead and download that. Maybe I already did. Nope. So this is an Excel sheet. Most of you have probably used Excel before. So the way that you read this is that we've got one column that represents a weather station ID, and then the name of that station, which is a city. And then we've got a few variables, kind of like an ArcGIS data set. We've got columns that represent attributes here. And this first attribute is the average date of the spring frost. Okay. And what this date is in days from January 1st. So what 85.27 means is that the average date of the last frost is 85.27 days after January 1st. I don't have that memorized what that would be, but you can use Google nowadays. 85 days after January 1st, April 25th. So what that means is that Edenton, North Carolina, has its average day around April 25th. The reason why there's decimals is because this is the average date of the last spring frost. And so, looking over a historic climate period, which I'm not sure exactly what it was, maybe it's the entire historical record. This was the average last day. Okay. And so if you had, 85, 87, 82, 81, 80, 80, 83, 88, and you averaged all those up, you might get 85.27. And then we have the latitude and longitude of that station. And finally, we have the elevation and the distance to coast of that station. We'll talk about how these values might have been calculated in a little while. I just need to predict today. All right. Now I'll open up. So this we can update. Well, I'm not going to update right now. So the content that's in this class, sometimes I don't know which one to talk about first. But remember, like 2 lectures ago, we started talking about like spatial processes, and we talked about first order effects and second order effects, and we talked about how a spatial pattern can be produced by the effect of a certain variable on itself, which was spatial autocorrelation, but also it might be created by the effect of one variable on another variable. In other words, distance from water might affect tree species, right? So we talked about both of those. So today we're going to be looking a little bit more into that and talking about ways to quantify relationships that are of the nature where one variable is related to another variable rather than variable 1 and how it's related spatially to variable 1. Okay. Like that's what we talked about last week with spatial autocorrelation. So, there's arguments for presenting which one before which other one. So today we're going to talk about this one. Although we've already talked about correlation a bit, we're first going to introduce that concept. So here is an example showing homicides and drug sale points in Washington, D.C. As you might expect, if we mapped homicide locations and drug markets, it's kind of small, but I'll make it a little bit bigger. There is some what appears to be a spatial relationship between those two. So where drug markets happen is where homicides happen in general. Okay, so that's an example of correlation. Two things happening together at the same place or in related places. And these principles, these correlation principles, they can apply not just to space, but they could also apply to other things. But in a geography class, we're going to look at the ability to correlate these patterns in space or occurring at the same location. All right, so we talked about correlation before, but in general, correlation is a set of statistical methods to measure both the direction and the strength of an associated pair of variables, in our case, spatial variables. Okay, positive correlation means that they both occur at they both occur together positively. In other words, as one variable goes up, the other variable goes up. The first example that we showed here was a positive correlation. More drug crime, more homicides, and vice versa. They're related. Inherently, correlation, when we talk about correlation, doesn't necessarily imply that there's a causal link between the two, or does it even imply one is necessarily the one that's driving the other? One could be driving one, or one could be driving the other. They'll both be correlated the same, no matter which way you look at it. Now, when we actually go to study these things, often we come up with a hypothesis that one is driving the other, and then we test that hypothesis. But are you talking about like cause and effect? Yeah, like in this case, we have drug markets and homicide locations, right? So what I'm trying to say is that just because they're related doesn't necessarily mean that one's causing the other. Although we could come up with a theory that that when there is more drug activity, it has an effect on there being more homicides. So negative means that as one variable increases, the other variable, the corresponding variable decreases, becomes smaller. So an example might be pollution decays downwind from a point source, so it goes down as you move further away from something. Its effect might diminish. Okay. And then finally, if it's random, then the two variables aren't related. Okay. There's little or no association between the variables. So here is a diagram of a few different cases of correlation. So going from strong positive correlation to, I guess, I would call this weaker positive correlation. For some variables, this might be considered fairly strong, but it's weaker than this positive correlation. Okay. And then strong negative correlation, weak correlation. So the x and the y here are the two variables in this case. Different than last week when the x and the y was the variable and the lag of the variable. Um, and so we're looking at the same variable in both cases. Here, for example, we might be looking at homicides and drug activity, or drug activity and homicides. If we're trying to make an assumption that one is causing the other, typically we refer to that as the dependent variable, and we put that on the y-axis. So if we're trying to say homicides are influencing drug activity, then we would put homicides here and drug activity here. But if we're saying the opposite, drug activity influences homicides, we would put homicides on the x-axis, or drug activity on the x-axis, and homicides on the y-axis.
So the dependent goes on the x?
The dependent goes on the y-axis. The independent goes on the x. Yep. Okay, so it becomes important, or it becomes something that we would want to do, is to measure this strength of association. Okay. So the strength of correlation is roughly estimated by the amount of spread in the scatter plot. So you can see that, the spread in the scatter plot. More spread, less spread. Strong, weaker. No correlation. Lots of spread. And as I mentioned last week, we can actually create a number that measures the distance from the line, the general line, and that's referred to as the correlation coefficient. So correlation, you'll hear this a lot. You know, if you study statistics, correlation does not imply causation. It only would support a hypothesis that they were causing one another. You need to actually look into the problem in a few different ways to really understand what's going on. But it helps us to begin to understand the relationship between two variables. There could even be a third variable that's causing both of those variables to appear the way they are. All right, so this is more about establishing if a relationship exists. So here is something that's often done in geography, where we take a variable and we plot it against another variable, but in this case it's a spatial variable. Here we've got the average date of last spring frost on the y-axis, and the latitude in the x-axis. So what type of relationship is happening here according to what we've talked about? It looks like a moderate positive correlation that's occurring, right? So we've got a scatter plot that shows that there is a trend here. And what does a trend show? As I go up in right. The further north I go, the longer it takes for the last spring frost to occur in a given year. So you can see that it's not a perfect spatial relationship. Can anybody think of some things that might be causing it not to be a perfect spatial relationship? I mean, generally, as you go north, what happens? It gets colder, right? What did you say, Elvis?
I just say colder.
Oh, yeah, it gets colder. So why isn't this perfect? As we go further north, is it always colder? What are other factors that influence? I know this isn't the climate class, but what's that?
Moisture.
Moisture?
Like,
yeah.
If you're buying a hotter body of water, even if you're more north, you can still be warmer.
Elevation.
Yeah. So moisture and distance to big bodies of water. Elevation, that's a good one. Yeah.
Observation of the weather,
The jet stream.
weather pattern.
Going from.
Yeah, the weather pattern,
El Nino.
prevailing winds, all that stuff. Yeah, there's lots of other factors that cause climate to be a little bit different than just being explained by how far north you are, right? So that's a good summary there. So this data that I've plotted here is the same data as in the spreadsheet, and here we have the northern latitude is the x-axis. In other words, it's the independent variable, and we're using it to predict the average date of last spring frost. So that's typically how we do it. So here is the same data in Excel. Okay, if you wanted to create this data in Excel, if you wanted to create this chart in Excel, maybe I shouldn't have created it, but you would just take latitude and average date of last spring frost, and you could go to insert chart, and you'd make a scatter plot right there. Now I formatted it a little bit different. Okay. The first thing I did was to make the axes smaller so that we're just looking at the data area. So you could, right click here, format axes, and you could set the minimum and the maximum. I did 20, no, I did 30. 30 and wait, which axis is this? Latitude. Oop. My axes. First of all, I need to reverse this because this is actually opposite. See how this is going with latitude on this one. So I need to first change these two around. So pull that. Now there's a button that just says select data. So right now I have switch row and column. Nope, that's not what I wanted to do. Remove. Okay. Trying to. Okay, so here's my X data. I hit this little button, and instead of it being the day of last frost, I'll make it be the latitude. And now there is a one-to-one relationship, but that's not interesting because, of course, an area's latitude is related to an area's latitude. Okay, so here we have it set up the way that it should be, and I could continue by adjusting the min and the max to make it look exactly like this chart, but we'll just get rid of that for now. So that's the chart in Excel. So we could go ahead and calculate the correlation coefficient. That is the indicator of the strength of the relationship. If it is close to 1, it's highly positively correlated, which ours is going to be closer to 1 than it is to -1. If it's close to -1, it's highly negatively correlated. And if it's close to 0, there's a lack of spatial relationship. On this sort of data, well, are these two variables nominal, ordinal, or interval ratio?
Those like the intervals,
they're real numbers, though they're not like, well, the average date of last spring frost, I don't know for sure whether it's interval or ratio, but it's one of those two. Longitude, though, is definitely interval. It's not ratio. So just because you're at 0 degrees longitude, or sorry, latitude, doesn't mean you lack latitude, right? It's not it's an arbitrary 0 that we've created. Like we decided that 0, and there's a good reason that we created the equator as the 0 mark, but it's not it doesn't represent the lack of that variable. Yeah, so both of these are interval ratio, and so we could use what the thing that we would use is Pearson's correlation coefficient. There is another, you can actually calculate a correlation coefficient on rank order data, on ordinal data, but we're not really going to talk too much about that. But yeah, the formula for doing so is not that much different than calculating what's called Pearson's correlation coefficient. Anyway, if you ever hear it called Pearson's correlation coefficient, it's referring specifically to interval ratio data. Now with nominal data, we could do cross tabulations. In other words, we could find out if, like, let's just say we had, well, we only had states and we had the count of something occurring in those states. Well, you can do really simple, population and states, and find out if there was a relationship between, well, population is not, population is still interval ratio, but still, one of the two variables is nominal in that case. And so you just basically have tabulations. And there are statistics to say, oh, are those evenly distributed within the states, or do more states have more population? So there are ways to do that. Okay, but we're talking about Pearson's correlation coefficient. So I think we mentioned probably most of this stuff. Small covariation, weak correlation. There we go. So here we've got different cases for covariation. If there's high positive covariation, you have lots of points in quadrant 1 and quadrant 3, and if you have negative covariation, you have lots of points in quadrant 2 and quadrant 4. And the correlation coefficient will be negative and high. And then if your points are equal in all quads, then they cancel out and the correlation coefficient is close to 0. All right. So we've covered that it ranges from -1 to 1 with 0 indicating no relationship. Okay, so let's look at the correlation coefficient for this data here. Okay. One thing we could do in Excel, pretty sure this works, right-click and you could say add trend line, and then you can make a linear relationship occur. So you can set the trend line right there in Excel. Actually, it looks like it only has the r² value. Pearson's correlation coefficient is sometimes referred to as r, and you could put the r², but not the r value. So there's the r² value. Now we could figure out what r is, right? So how do we figure out r from r²? Yeah, so we could say equals 0.7252. Oops. SQRT of 0.7252. Now what happens when you square root a number that's below 1? Does it get bigger or smaller? Yeah, it does. If it's below 1, it gets bigger. And so the correlation coefficient is 0.85. Also, what happens if you square any number that is negative?
Imaginary numbers.
No, square, not square root.
Oh, okay. Oh, it makes it positive.
Exactly. So R squared is always, and we'll explain exactly what R squared tells you here in a second, but R squared is always a positive number. So we can infer that this is positive. Why? Why?
So it's going up to the right?
Yeah, it's going up and to the right. And so we know that this number should be positive. If the trend line was going this way, we could infer that that should be a negative number. So we can confidently get R from R squared in Excel, even though it won't report it to us directly. But we can know what it is. So in this case, R is 851587. That's a pretty high value. So it's a lot closer to 1 than it is to 0. So there is a spatial relationship here between these two. I'm sorry, not a spatial relationship. There's a relationship between these two variables. It's spatial because one of them is space. One of them's latitude. Okay, now let's get this data into a GIS, into ArcGIS Pro. So ArcGIS Pro and ArcMap before it doesn't really have a problem reading in Excel data. So we can go, I'm going to make a new project. I'll just call this regression 518, or no, I'll just call it regression. Because then I have to say 418 or 518. I'm sorry, it's 517 to get the right number anyway. Close the Python window here. So I forgot where I saved it, but I can add some data to the map, and I think I just put it in downloads. Is it this one? But there it is, right there. So I can add that data to the map. Required Microsoft drivers installed. I have Excel installed. I did this on my other computer, worked just fine. Dead data, let's see. Maybe go inside of it. Okay. Well, that stinks. So what we could do is, instead of, it should read an Excel file. I don't know if some of yours do or not, but it looks like it's looking for some Microsoft information. So it's easy enough, though, to export from Excel into another format that I'm sure ArcGIS will accept just fine. So we're going to take the data and we're going to export it as what's called a CSV. CSV stands for comma separated values. So now I'm going to save in the same directory, I'm going to save a file called dlsf_data.csv. So I'm going to hit save. And now I've saved that out as a CSV. I'm going to close it here just to make sure, and then open it up. DL, make this bigger.
It's a CSV, right?
Yes, CSV. Let's see. I saved it in the same location, right? Oh, usually need to hit refresh. Okay. There it is, right there. So open that up, and now I have a standalone table in my table of contents. Thus far, it's just a standalone table.
Is there any difference if you did get it from Excel?
It should just work. Can you open up the attribute table if you got it to work in Excel?
Yeah.
Okay. I don't know why I have these 2 extra fields here. We'll just ignore them for now. But all this data should be the same. I wonder if it rounded some of my values.
It looks the same as what I got.
Okay. Go back to the original. Yeah, no, those values were already rounded. And for our purposes, that's fine. Okay, so we've got all this data in a CSV. Ben, do you have a question?
Where'd you get that from? I mean, I'm following along, but every time you click up there, I'm looking at my,
Where did I do what?
the
The add data right here.
ad data.
And then I went to where it is on disk. So I put mine in, I just downloaded it.
Data from Pat or just data?
Just the first one, data. Add data to the math.
Data. For myself,
Yep. And then you could right click on it and you could say display XY data. And this opens up a tool. Hopefully. And then you could take the CSV or the Excel, whichever one worked, and then you can fill this out. And this is the feature class where it's going to output it to. Okay, it's going to output it to regression.gdb. So it's the local GDB. So if you want to change the name of it, we can make it sound a little bit better. I'm going to make it called, I'm just going to make it called this. I don't need all the extra part. Date of last spring frost underscore data. Now, is longitude and latitude correct? Longitude is X, latitude is Y. Yeah, that's fine. All right. Now, what we do here is we need to specify, if we hover over that point, the coordinate system, this is the coordinate system of the input locations. It's also going to be the coordinate of the output data. And so when we want to make sure that it's in the same one. Typically, most just CSVs that have latitude and longitude are using what's called WGS84. It's the most recent worldwide data. That's what it means. And the latitude and longitude means that it's unprojected. It's not in any coordinate system, any projected coordinate system. So now you just hit run, and it'll run. Now later, when we do some analysis with this, we'll want this in a projected coordinate system. I think I talked about this both of the last 2 weeks. But if we want to actually start measuring distances from things, we need it to be in a coordinate system that measures distances accurately rather than latitude and longitude. But we need to import it in the coordinate system it's in. So we have that. So now we have those data points. And most of the tools that we're going to be running today are under modeling spatial relationships. Okay, so they're under the spatial statistics tools. We've done some of these other toolboxes the last few weeks, analyzing patterns, mapping clusters. Now we're going to be looking at modeling spatial relationships today. So now I have the data in there. So that one has a pretty strong correlation coefficient. latitude versus average days of last spring frost. Here's an example of another data set that has a weak but still negative relationship, right? So if we look at the cost of living and the percent growth of foreign-born population, we see that in general, as the cost of living increases, the percentage growth of foreign-born population decreases. But there's a lot of spread. In fact, it's more like, if you were to actually describe this pattern, you'd say that as the cost of living increases, the differences between the percent growth of a foreign-born population in places goes down, but it's and down here there's no relationship, and then it seems as we go up here, it seems that it trends downward and kind of holds steady.
Can you also say too that at the lowest cost of living, they got exponential growth? I mean, the population burst because when they poor, they can live in that area, but as you go more, it might be you correlate to that to a particular area where that maybe really real cheap.
I mean, this graph doesn't show that. What this graph shows is that in the low cost of living areas, are all sorts of foreign-born populations, from very low to very high. In the high cost of living areas, you only get low foreign-born populations, basically. That's what the graph shows. So, I mean, if you did want to do a test about this, you could perhaps divide these up into ordinal areas. You know, basically say cost of living, low cost of living, medium cost of living, high cost of living, and then look at the differences between those three groups. But using a correlation coefficient strictly doesn't produce a strong correlation at all. All right, so the first thing that we want to do after we calculate a correlation coefficient is to describe the nature of the relationship, and we can do that using a simple linear regression as the first step. Sometimes it's referred to as ordinary least squares, or OLS. See, it's one of the tools here on our GIS Pro. The ordinary least squares tool is right there. So the ordinary least square tool, it assumes that one variable influences or affects another, or that a functional relationship ties one to another, unlike correlation. So what it seeks to do is to explain the variance in one variable as a function of the variance in the other variable. So this isn't unique to geography. People use regression all the time in lots of different research areas. I have a few examples listed here. But when we apply regression, we should have studied the problem already, looked for a pattern, and we should have a clear rationale. In other words, we should have a reason for building a model and saying this variable influences this other variable. Okay, we have, when we have just two, sometimes we would call it a bivariate regression. In other words, if we have one independent variable explaining one other dependent variable on the y-axis, that's called bivariate regression. And that's what we have in this case so far. Okay, we have the latitude trying to explain the average date of last spring frost. Okay, and so this line that gets created, I've already created in Excel. Well, I don't know where that, oh, I closed it up. But that line that I created earlier in Excel is that functional relationship. That is the mathematical relationship between the two variables. We can do that in ArcGIS too. So here, we could take the ordinary least squares regression tool, click it, and choose the DLSF data and specify the feature class, the output feature class. I don't know why it isn't giving me the choice of choosing a field. Maybe it's because of the way I created it.
I loaded that one, using what you did in, Team Managed, they automatically put everything on the phone.
Just a second here. Trying to figure out.
What do you want the data field?
Oh, I don't have any integer fields. I think it's because I did it as a CSV. It just basically assumed everything was double. Does yours work when you choose from Excel?
I can choose SID or.
Yeah, because you were able to import it as Excel. So what I can do to fix that problem is create a new field. It's required to have a unique ID field. So I can create a new field. I'm actually going to get rid of both of these fields. Can I do that? Because there's no reason to have them. Well, I'll do that later. But I can call this field station ID, and then I'm gonna make it a long and save it. And then what I can do here, I can delete these two fields that don't have any information. So now I have this station ID field, and I can. What's that?
In that station ID field, the along.
Yeah, I made it a long. So now I'm going to make it have the same value that's in SID. So this is actually technically a decimal number, even though there's no decimals. So I'm going to run it. It's a double. And now I'm copying the SID value over into the station ID so that I have an integer value. So when I run ordinary least squares, I'll be able to choose the station ID. So that's why I had to do that. What's that?
Did you just copy it? Is that like, can you show me real quick how you did that?
Okay, I right-clicked and I said calculate field, and then I just under station ID I double-clicked the SID, so it pulled up. It's just a simple Python expression, SID exclamation point, SID exclamation point. What's that?
Maybe, but with my CSV file, it won't let me add fields or anything like that.
Did you turn it into a shapefile yet? You need to run on your CSV file. You need to run display XY data.
Right, I did that.
Okay, so don't add the station ID to the CSV. Add it to the shapefile.
Okay, I'm in the wrong application.
Yep.
Okay, yeah, so that's what.
All right, good questions. So what we're going to do here now is to move this over. And maybe actually, I mean, at this point it doesn't matter too much, but yeah, so we'll just keep going. So right now, although we're using longitude as one of our variables, or sorry, latitude, we're using latitude as one of our variables, it's not actually inherently spatial. In other words, it's not measuring any distances yet when it does it. It's just actually using the latitude value. So unless we're measuring distances, we don't have to put this in a projected coordinate system. But later, when we talk about a few other methods, ArcGIS will actually, there is a way for us to tell it, hey, ArcGIS, you choose spatially a way to make the regression formula. You choose distance, the coordinates basically for it. And then in that case, you do need it to have it spatially you do need to have a projected coordinate system. But for right now, we'll just leave it the way it is. Okay, so ordinary least squares, DLSF data. The unique ID field is going to be station ID. The dependent variable, what will that be? Dependent. Yeah, the frost date. And then the explanatory variables, or sorry, no, actually this is the dependent variable. Yeah, what we're trying to predict is frost day, yeah. So the explanatory or independent variable is latitude. And then we can actually export a report file. There's a lot of information that'll just be put out on the screen, but I'll still do it. Folders, we'll call it, it's going to make it a PDF. We'll call this report 1 underscore, I'll just call it latitude. Latitude only OLS for ordinary least squares regression. Oh, at the, there we go. All right, so this is this actually contains most of the information right here that's in the report. But here's the link to the report, which we can also open. I'm gonna open it in Chrome. Okay, so there's the report, and you can see that there is a familiar number right here. Here's the R squared value that we got in Excel, and we could calculate the correlation coefficient also from that. There should be yeah, there it is. So here is the scatter plot. It's kind of small. Okay. There's a lot of information here, and we'll talk through what each of these, what each of this information tells you. Well, not every single thing, but a lot of what it tells you.
I have a quick question.
Yeah.
Is there like a set number, you know how you said we thought that this was a pretty a moderate positive relationship? Is there a number if it's under 0.7 is that weak, and if it's over 0.8 is that strong? Is there a cutoff, or is it kind of it's dependent on?
Well, there is a significance level, like a significance test for the relationship, and here the asterisk indicates a statistical significant probability. But also in practice, there's a practical, does it help me type of a question, and that's more related to your particular question. So if it's not significant, it's usually, it means that there's not a relationship. But even if it's significant, you have to ask yourself, is this predictive power enough to do what I need to do? And that's another question. In other words, one of the things that the outputs tells you is how closely, given a certain X value, how well you could predict a Y value for that particular relationship. And that has to do with this spread, right? If we go look at if we go back to look here. So this, you can imagine the line through this, and the spread is how far away these points are. And so if for a given latitude you can predict the average spring frost between what looks to be, about, see if I go to 60, and that probably is going down to about 20. So somewhere between, for a given latitude, I can predict the temperature plus or minus, plus or minus 30 days. Even though it's significant, is that something that's going to help me solve my problem, whatever my problem is, right? if I'm trying to decide when to plant, a 30-day window on that relationship might make it so that it's pretty much useless. If I'm going to always be planting 30 days later than I think I need to be, then it might be useless. But maybe there's some other application where it would be helpful. So that's what I'm trying to say, is that this spread, even though there might be a significant relationship, this spread that shows up is what's causing it to be, moderately strong connection. But what does moderately strong mean for you? Well, it means that there's a spread of about 30 days. See what I'm saying?
Yeah.
Okay. So let's talk about a few more things, and we'll come back, and I think that question will be better answered. So the first thing that's created by that line is something that's called the regression equation. Okay, that's a mathematical formula that's applied to predict the dependent variable you're trying to model. Okay, so here when we say x and y, we don't necessarily mean coordinates. We're talking about the values. So when we show this this regression equation, the x's here are any explanatory variables, and you actually can have more than one. So we could decide that we're going to use both the latitude and another variable. You mentioned a few before class, humidity, elevation, those sorts of things. And we could see if we get a better model to explain, in this case, the date to last frost. Okay. All right, so so each independent variable is associated with a regression coefficient, describing the strength and the sign of the variable's relationship to the dependent variable. So in this case, we only have one. Let's look at the coefficient with latitude. So in other words, that's this value right here, the coefficient. So that's its relationship with latitude. In other words, a 1 degree change in, sorry, not a 1 degree, a 7 degree change in latitude causes a 1 change in the date of last frost. Okay, the date of last frost. So that's the nature of the relationship. It's a 7-to-1 change. We can kind of see that in the slope of the line. All right, let's try to run this again. Instead of just using latitude, let's throw in the elevation. And I'm going to call this, well, I called the other one ordinary least squares 2, I guess. I had a better one before, but I'll call this 3 and run it. I kind of messed up latitude only. I should call this underscore elevation. Run that again. What's that?
So I got mine through an error.
When you tried to run it with elevation?
Yeah.
What does the error say?
Oh, I think it was trying to override because I didn't change the name of my output file. So
Oh, okay. So now we can see that it's created a whole new model. You'll often see that the coefficients for the terms will change when you throw in other things. So now we have a different coefficient for latitude, 6. So in other words, now only a 6 degree change in latitude will cause a 1 difference in day, and an elevation change of 0.008. This elevation is in feet, I believe. So a little bit of change in feet will cause a little bit of change in that. Now look, both of them are significant though. So we had both of them significant. Okay, there's a few different things that we can start to look at here. Look at the warning. First of all, there's a warning that it doesn't contain projected data, which doesn't matter so much for ordinary least squares, but it would matter later. So that's why it's warning us. Look at this other warning. What does that warning say? This is one reason why I did the autocorrelation class first. Use the spatial autocorrelation tool to ensure the residuals are not spatially autocorrelated. Now, first of all, we need to learn what a residual is. Maybe some of you have taken a statistics class. This is actually a map of the residuals. I'm going to turn one of them off and one of them on. So this is a map of the residuals when we included elevation, and this is a map of the residuals when we didn't include elevation. There's really not too much of a change there. There is some changes that are occurring. So what's a residual? Well, we talked about the dependent variable, the independent variable, the regression coefficients. We talked about the R squared. How did the R squared change, actually? Let's look at that in the second one that we ran. The R squared value is right here. It went from 0.72 to 0.80. So it went up. So what does that tell us?
Made it strong.
Yeah, the relationship is stronger. Okay? Specifically, R squared tells us something that we'll talk about in a second. But it does mean that the relationship got stronger, for sure. All right. Residuals right here. Residuals are the unexplained portion of the dependent variable. In other words, if we can think about the relationship that we just created as that line, the residuals are all the differences from the line back to the model, the idealized line that was created. So they're showing us the differences. Now, if we map those residuals, we can see that there's a little bit of a pattern here, right? What do we see in our residuals? Like, where are more of the negative residuals versus where are more of the positive residuals?
Towards the coast.
Yeah, I think so. I think that's in general. The negatives seem to be close to the coast, except for like maybe that's an exception because that one's close to the coast and it's a positive residual. And then the other positive residuals seem to be clustered a little bit more in the mountains or the fall line, like right through here. And the negatives seem to be right through here. Okay. Now, when we see any pattern in our residuals, what do you think that means? If we were to look at and say, well, there's a pattern in our residuals, what could be causing the pattern? Like, why does the pattern exist? What does that imply about the relationship that we've established?
Do they have a cause and effect relationship?
Well, there may be another causal variable that we're missing because there's some pattern that exists that we might be able to say, oh, well, that's another thing. And so distance to coast, that's not a mistake that I kept that in there. So distance to coast looks like it might be another causal pattern in our spatial relationship. And so we could check that off, say distance to coast, and run that again. I should have saved it as even a different number. Okay, so I ran it again, and I think that it made it so that there's less pattern in our in our residuals. We still see higher residuals, both positive and negative, near the coast than we do everywhere else. It seems like there's almost no pattern left. So right through here, though, a lot of our biggest residuals are right in this area. Got some big positives and at least one big negative right in that area. Also, we could look and see, we could look at the strength of the relationship there. And we see that we've gone up to 0.82. So we've got even a higher value. And if we scroll down here, we still get the warning, spatial autocorrelation to ensure the residuals are not spatially autocorrelated. Okay? So that's the tool that we ran last week. In order to run that tool, our data would need to be projected. So at this point, let's go ahead and project that data. Okay, so there's a tool called Project in data management. We could take our, let's take our original data set, the DLFS data, and we're going to change the coordinate system to be something that measures in real distances. So it needs to be a projected coordinate system, and it should be an equidistant coordinate system. So there's probably a UTM coordinate system that would be appropriate, but it would still, some of these would still fall outside. I think, well, I think maybe I will do that. So UTM, WGS 84, Northern Hemisphere. Let's look at a UTM map. And let's look for the UTM. Oh, this one's good. The UTM coordinate, I mean the UTM map that's closest to this area. Looks like this one. That's 17. See how that UTM zone captures most of our data? Now some of our points are outside of there, right? There's a few of those points that lie on either side. But that's not a huge problem. The UTM zones, they're created in order to ensure that there's a specified level of distortion that occurs inside the zone. So if you go a little bit outside the zone, there'll be some additional distortion, but we're not going that far out, right? So it looks like just these points are outside, just those points are outside. So I'm going to choose zone 17 north. WGS 84, 17 north, okay. And I don't need to change the geographic transformation because that has to do with changing the datum. So if I keep the datum the same, I don't need to specify a geographic transformation, and I can just run this. That's a fine name for it. All right. I'm going to delete these guys real quick. Yeah.
I did a hotspot analysis with a heat map relationship on there and an unusual amount.
A hotspot of what?
A hotspot data goes point with a heat map relationship on top of it. This is unique.
Yeah, I got the hotspot part, but what did you like? Hotspot of the.
I did the hotspot of the points that we originally started with, and then after that I did the symbology with a heat map, and it moves certain entities together, and they got a very this is unique now. See,
Okay.
so I'm just playing around with this to see
Right.
I look for coefficients and all that. If I just took all those to be a bunch of dots and just apply what you told us before,
Yeah.
and but anyway, then
Okay, so I'm going to run the same information. I'm going to average date of last spring frost, latitude, elevation, distance to coast, and this will be elevation to coast. I'm going to call this all that. Okay, I'm going to run that. Now I don't get that first warning. I don't get that first warning about unprojected data. So that's what I was really looking for. Okay. All right. So if I want to now run the Moran's eye, which is under Analyze Patterns, Global Moran's eye, spatial autocorrelation on the residuals. So I could take the residuals, and I've got a field called residual, and I've got another field called standardized residual. Either one's fine. The standard residuals tell you the residuals are in real number values. In other words, a residual of 3 means that at that location, the model predicted a certain value, and the station had a certain value, and it was off by 3 units. In this case, it would be 3 days, 3 days. Yeah, 3 days, because it's in days. Okay. The standard residuals tells you how many standard deviations it is off. So either one of these will be fine. Let's do residuals and generate my report and run that. And let's look at the results here and decide whether or not this is spatially autocorrelated. So are our residuals dispersed, random, or clustered? They're random. That's good news. Okay, that means that there's probably not any more lurking spatial variables to worry about. Okay, we did it just fine. In contrast, let's go back really quick and look at doing the ordinary least the OLS on the same data set. Sorry, on the same data set with just the elevation. Yeah. Dependent variable is latitude. Sorry, not just the elevation, just the latitude, and see what we get. So it's latitude only.
Shouldn't the dependent variable not be latitude then? It's only picking latitude.
Oh yeah, latitude. This is dependent variable is this. Sorry, I messed up. Thank you. This is latitude only. I'm going to call this latitude only. So I can keep track of it. So that's latitude only. And then let's see if that one is spatially autocorrelated. The residuals are spatially autocorrelated. So go input field, average the residuals, generate a report, run it. So those residuals were clustered. So it's always a good idea to run and see if your residuals are spatially autocorrelated. So with just latitude, the residuals are clustered. In other words, there's some sort of spatial pattern associated with your data. Now, what if they were dispersed? Well, then there's some sort of spatial pattern that you might have to look at to try to explain your relationship better. But if they're random, it means that if your residuals are random, it means that there isn't a spatial pattern and you're good to go. Doesn't mean there's not some little spatial pattern that you can pull out, but those three, if we include all three of those, that's this one, we get a pretty high R-squared value, and there is not a significant pattern to the residuals. So that's good. All right. Finally, we talked about all these other ones. The regression method, the p-values tell us how significant it is. How significant what is? Well, if we think about it as a hypothesis test, the hypothesis test is that the coefficient is really not zero. Okay? In other words, if the correlation coefficient, if the relationship between these two was really if there really is a relationship between these two, the pattern that we see couldn't be created by chance. Well, it could be created by chance this many times or this often. That's what the p-value means. So let's look at the p-values that we created. Those are in here. Go back, catalog, we look at history. So ordinary least squares now for all of it. So here's our p-values. They're all significant. One is pretty close to being insignificant, at least at the 0.05 level. See that? That's elevation. So we can see that latitude and distance to coast are more significant, but they're all three a significant value. The adjusted R-squared is 0.82, and we tested the Moran's-I and it worked. So this is a pretty good relationship that we've established. Latitude, elevation, distance to coast. And here we can actually look at, now we can understand this graph a little bit more. So this is a scatter plot of all three of the variables related to the average date of last spring frost. So this is latitude, the one we did originally, but this is a scatter plot of elevation, and this is a scatter plot of distance to coast. So each variable individually and its relationship to the average date of last spring frost. Now here are just the residuals plotted in a scatter plot, predicted versus standard residuals. And you actually want this chart to be random. In other words, you want there not to be any pattern between your predicted value and the standard residual. So in other words, if there was a pattern here, what that means is that in very high areas, you might see more residuals. Or in very low areas, you might see more residuals. And basically, go back to here. If we ran this data through the same analysis, and we came up with a line that looked like this, let's say, then what would happen is in the low area there would be more residuals, and in the high area there'd be less residuals. So that's an example of a residual pattern. So your residual pattern means that there's something about your relationship that isn't modeled very well using a line. That's what it means. Okay. These are how you calculate the residuals, the distance to that line. Now, in two-dimensional space, that is pretty easy to conceptualize. But what we've done is when we choose to include multiple variables, and here we've included latitude, elevation, and distance to coast, what we've done is made it so that there's four-dimensional space now, because we've got our our y variable and three x's. So we can still establish a linear relationship in four-dimensional space, but we can't draw it. But the math still works. All right. So what do some of these other values tell us? So we can look at the y-intercept. The y-intercept is the value when x is equal to 0. Okay. So look at our y-intercept for our result. So it's right here. No, well, it is in here. Here's the y-intercept, negative 114.7195. Now for just elevation, it is negative 152.0. Okay. What that's telling us is that when the x value is 0, in other words, let's just go back to if there was just elevation. Sorry, not just latitude. When latitude is 0, the date of the last spring frost is negative 152. Here it's negative 114, but that's what we included all of them. Does that make sense? Is that even a real number? What day would negative 152 occur on? It doesn't make any sense, right? So you do have to think, when you're interpreting your y-intercept value, you need to think, does y exist? Sorry, does that value exist within your domain? Our domain is between 29 and 37 degrees latitude. That's where all of our points fall within. So we can't really say that this spatial relationship works anywhere outside of our domain, what that means. So it doesn't work out there. That's called extrapolation. When you take a mathematical model you develop like that and try to predict what the value would be either way up here in the extreme north or way down here in the extreme south, it doesn't work. It's outside of the domain. That's what that means. All right. So the slope is that's the regression coefficient. That's what we've already said. So the slope between latitude and the date of the last spring frost is that. The slope between elevation, slope between distance to coast. Those are all fairly small, but remember that they're scaled differently. Distance to coast is in miles. So we've got, let's look at our table. Distance to coast is, the highest value is 298, 300 miles from the coast. The lowest value is 1.148. And so those values are differently scaled than latitude, which ranges from 28 to 38, 29 to 37, basically. All right, so
So are these results telling us that it's mostly influenced by latitude, next by distance to the coast, and then finally by elevation? And these are the coefficients, like, since latitude is 5, the distance to the coast is 0.04 and then 0.003. Is that something we can assume?
Yeah, so now these numbers, I guess what I'm trying to say is these three numbers under the coefficient, those are dependent on the scale of the variable. But the probability follows that same pattern in this case, uh, where this one's the smallest, that one's the second smallest, and that one's the third smallest. And so that's really the number to look at to see how significant it is, right? So
the smaller the number is your probability, the more significant the variable is.
right. So if you were to look at just the coefficient, that's affected by the scale of the variable. In this case, well, actually, this number is, yeah, this number is bigger than that number. So there's an inverse relationship here, but that's not always the case. You could have, in other words, if elevation was scaled like in inches or something, then this value would be moved over. It'd be 0.0, well, it'd be moved over almost inches, or there's 12 inches, not 10 inches, but it'd be almost moved over a decimal place and adjusted a little bit.
The number should stay relatively consistent, though.
Yes, the probability number will stay consistent because it's based on the actual spread, the relative spread, and it's not fooled by a different scaling value. It's looking at the variance and how one varies with the other. It standardizes that. That difference. Okay. There's a few things to look in here. Like this report actually does a pretty good job at describing lots of things. So this VIF right here, that's the that describes it right here, the variance inflation factor. Basically, what the variance inflation factor does is it looks at the correlation between two of your variables and decides if one variable is redundant. In other words, it's providing information that is already there. Even though it might be significant, it might be really related to another variable. In this case, all these values are below 7, which means that there's not a whole lot of redundancy between the three variables. So they're all unique to each other. Okay? They're all providing unique information, even though elevation isn't providing as much of the explanation of the overall model. It is providing some information that's not redundant. What that means. All right.
Pretty much, if you had a high VFI, you wouldn't need to test that factor because it's already been represented in another factor.
If you have a high VFI, the best practice is to remove that variable, rerun the model, and lots of times what will happen is that you'll get just as strong a relationship without that. What that means is that those two, the pattern created by those two variables is almost the same pattern. So there's either one is explaining the other, like if you were trying to predict unemployment and you had in your variable, you had poverty levels and I don't know, something. It's hard to come up with an example here, but let's say you had distance to coast and you had longitude. I'll bet those would be pretty related because most of the data has, the distance from coast is the distance this way. Some of it is different, but not all of it. I don't know. I mean, I guess we could try running that one and see. So we got we're going to throw longitude in there too and see if that causes any problems. I'm going to call this test. Run that guy. Yep. See now longitude. Look at how high the that one got over 7.5, and distance to coast is now 8.66 for the VIF. So in our particular instance, it's not everywhere, but in our particular instance, longitude, which is the western, as you move west, in general, you get further away from the coast. Now, that's not real. So you don't always get further away from the coast as you travel west, but it is in our data. So in our data, throwing in longitude kind of threw this off. And that's why both of these numbers, the VIF number is high for both longitude and distance to coast, is because those values aren't unique. And also, it made it so that both longitude and distance to coast were no longer significant. And distance to coast was really insignificant. Longitude was kind of insignificant.
So
I mean, was still insignificant. What's that?
if you were wanting to delete one of these out, which one would you delete out? I would assume it'd be distance to coast, right? Since it's
Yeah. Okay, so you're right. Just looking at these numbers, this is actually a pretty good lesson. So just looking at those numbers and not caring about what these values actually represent, just looking at those numbers, yes, you would throw out distance to coast. The problem is that if we're really building a model, longitude shouldn't have any real, like, if we can't think of a reason why longitude should have an effect on the last day of spring coast, then we shouldn't build a model that includes it. It will definitely really hurt our model if we tried to make it predict a little bit outside of the region. It would really screw it up. Like, let's say we tried to predict the average day of last spring frost in Missouri all of a sudden. Well, it's really going to be messed up because longitude doesn't really have an effect on that variable.
But neither does distance from the coast though either. So you can delete both of them out, right?
Well, distance to coast, you can make a logical connection that influences humidity, and that humidity causes. There might be a better thing than distance to coast. You're right. There might be a better one. What I'm trying to say is that, to me, longitude shouldn't have an effect on the average date of last spring frost. Distance to coast, I can make a logical argument for that. And therefore, I feel more comfortable about keeping that in the model. The last thing to do would be to actually run it one more time without distance to coast and see how much of a difference it made in the overall scheme of things. So I'm going to run it one more time here and look at that report. So now if I run that, and let's look at the overall adjusted R squared. It's 0.83 something versus, I forgot what the other one was. It was 0.82 something, right? So we're really
2.7 versus
2.7 versus 3.5. That's like, you're right. That's a really small difference. And so, I don't know, what happens if we take them both out? But to me, even though that's a slightly higher value, I think it's just a mistake in the geography of the region that we've chosen. So for the region that we've chosen, it just so happens that as you move west, that relationship changes better than saying distance from coast. Can anybody think? I actually think that's probably because of basically the difference in the water temperature of this area versus this area. To me, that makes more sense than that. So
find, like, in your Missouri example, that I would think that longitude would still kind of matter is because of our east-west, like, wet, the wet dry line, that, as you go more west, you get more and more dry.
Yeah. Yeah.
And maybe, I don't know.
Yes, you're right. As you go more west, you get more dry. So maybe it would make sense to leave longitude in there. I don't know, but yeah, these are the types of questions that you look at and you run in and you come up with a solid scientific reason to leave longitude in, and you could make an argument for longitude, right? In reality, I guess we shouldn't be including Missouri unless we actually have data from Missouri. So yeah, this area right here, longitude is a slightly better predictor than distance from coast. But I think it has a little bit more of a, it'd be interesting to see through time if that's always the case.
Right.
But yeah, that's interesting. But distance to coast, definitely we can say that distance to coast and longitude are related. So for whatever reason, whichever one we think is more scientifically valid is the one I'd probably leave in the model if I was doing the study, because they're very, very similar and they're telling you almost the same thing. And so you don't want them both in the model. So that's the summary there. Oh, I messed up. Okay. Okay, so yep, covered that one. So finally, this is just a little diagram that kind of talks a little bit more about this relationship between the explanatory variables and the response variables and what R square means. So I think we've covered this well now, but if you think about all of the water in a bucket, when we build our model, what we can think of is that the variance is all of the water that could be in a bucket, and we could have a sponge that we squeeze out and put in the bucket, and it sucks up a portion of the water. And so one way to think about the R squared value is that it's a ratio of the amount of variance that's explained by the relationship to the overall variance. So the variance of the residuals as a relationship to the overall variance of all of the values there. So it's a percentage.
The R squared?
The R squared is a percentage. And so in our case, we have a value of around 82, 83%. What that's saying is that around 82% of the variance in our Y value is explained by the variance in our different X's. We have 3 X's. And around 82% of the variance is explained. Sorry, were you about to say something?
So X always affects Y when you take out the exponential and to S.
Yeah, when we use linear regression, we're saying that X influences Y. In other words, the variation in X explains the variance in Y. Another way to think about it. Now I cited where it came from, but it's another. So here's kind of a graph showing how R squared changes. So here is 90% of the variance being explained between 2 variables. Here's 50% of the variance being explained between 2 variables. And here only 10% of the variance is being explained by 2 variables. What?
Two next variables, we have 2 trend lines. We have 2 trend lines on 1 block.
No, you actually don't have to use a linear relationship. you could specify a nonlinear relationship, which is possible, but we're covering the linear relationship right here. If it actually looks like there's two different relationships, it's best to just divide your data up. You know, like if your data spanned the whole world and it looked like you had a totally different relationship in Russia than you did in the United States, just divide it up and do one regression equation over there and another regression equation for the other area. Okay, so this was really the problem that we came up with the longitude and the distance to coast. That really is a problem with, or a question of overfitting, right? Like if we make our model so specific to a particular area, then it makes it less portable. And what you just brought up, Elvis, like, well, can we have two different lines? It's likely that we're overfitting at that point, that we're making our relationship too well, fit too well. But there is a way where, when space is the question, we can throw in space as a weight in a regression equation, and that's called geographically weighted regression. So I'm going to come back to some of these others and just show that real quick. So that's the very last slide, because it kind of seems like we're going on this tangent anyway. But so if I've got the data here, I can run this tool called geographically weighted regression. And what geographic weighted regression does is that it basically changes the regression equation based on where you are. And so it looks and establishes small relationships with pieces of the data in a geographic pattern. It makes it a little bit harder to interpret, but we could do the same thing with our data. We could choose the average date of last spring frost as our dependent variable. And then down here, we should not include values that have to do with space, because they're already going to be included in the regression equation. So we wouldn't include latitude, we wouldn't include longitude, but we could include elevation and distance to coast. And then we have to specify what a neighbor represents. In other words, what areas are we going to pick? So we could choose to do a certain distance or a number of neighbors. Let's just do distance band and say, let's go with user defined. Actually, I'm just going to hit number of neighbors first. Let's choose the defaults. I'll run this and see what we get.
You did it on Golden Search?
I did it on Golden Search. That means that it's choosing the value for us. So we can interpret some of these numbers the same way. So for example, we're still going to get an R squared. It's 0.85, but we're going to get a. So what it did was it ran with 30 neighbors, 76 neighbors, 48 neighbors. It ran with a bunch of different values, and it looked at the AIC and how that was changing. So it ended up using 523. So it ended up using 33 neighbors as the kind of the sweet spot there. I didn't output a report, I guess. Yeah.
Kind of weird that they won't let you do a report for this one.
But it does actually show some additional charts that the other tool doesn't. So it's kind of like the report. So here's that, you know, the relationship between elevation and distance to coast, and here's the distribution of the standard residual. It's kind of like the report. These were all in the report. See, those are pretty random. So those are pretty good. The residuals look similar. But this is because what it's doing inside of the geographic weighted regression is that it is using geography in the regression equation for you, and it's basically coming up with a different regression equation for every set of neighbors. So for every 33 set of neighbors, it comes up with a different regression equation, and it factors in the location for you. Yeah. So one of the weaknesses is that it's not as easy to interpret because latitude no longer shows up as a value. Also, we don't have all of the we're not able to interpret the individual values in terms of the coefficients. We don't know how much everything is affecting the other values. We can, let's see, production locations. So the way that we would actually use this is that we would have some, we would run this on some predicted locations. In other words, we have some unknown values that we were trying to predict, and we'd come up with a value to map to those areas. With the standard regression, we could map any location based on it. If we had the x and the y, if we had all the other x values, we could map a y value based on that. Whereas here, we don't know what the coefficients are, and so that's one of the weaknesses for geographic weighted regression. There's a few other problems with geographic weighted regression. One is that you don't want to use it with small data sets. In fact, our data set is getting close to being too small to use geographic weighted regression for it. Okay? You want several hundred features for best results, not appropriate with small data sets. We have 200 and something, so I guess that's technically several hundred. Is that how many we have? No, we only have 76. So technically, we shouldn't be running geographic weighted regression. It's a new tool that they created more recently. Okay, so let's go back up. Interpret some of our results. So if we multiply r squared by 100, then we'll get the percentage of water explained by the sponge. Yep. So r and r squared are related. One is just a square of the other, but they're different and they have different interpretations and purposes. So r squared helps us to specify how much variance is explained, and r tells us about the strength of that relationship and its direction, because it's usually positive or negative. It doesn't imply a causal relationship.
You said R was variance, and R squared was what?
R squared is the amount of explained variance in the model. R is just the level of association, the correlation coefficient.
Hey, Dr. Ray,
Yeah.
I just sent you something to your, outlook, and I actually charted all those things you said based on each one of those things you talked about. Could you point it up real quick?
You sent it to my email?
Yeah, That was another one.
Hmm.
It's a Word document.
It's not showing up. There's no attachment on my end. It says updated heat map. It doesn't even show as an attachment here. Oh, this one. Okay, so yeah. So this is basically just a heat map of where the stations are. So we have more stations in this area than we do in other areas.
There are 3 pages. I think you got 3 pages. If the map each one is being talked about, it shows the dot. You ain't
Okay.
got to pull it up.
Then this one didn't have the attachments.
Okay, that's the one right here.
There's one that didn't have an attachment, Elvis.
Okay, so this right here is, that's right here. Okay, this one I just sent you, says, you see don't have a section to it?
Yeah, the one that says heat does have an attachment. Okay, so is this showing me what you ran to get this result?
Right, and she was talking about, the last one you just did, I ran around that 2 weeks.
This one right here?
Right, that was that one there, but I had to give a proportion based on the right. I wouldn't.
So what does the size of the dots mean?
The size of the dot means the proportion of the how they affect that particular, um,
Because here it looks like the size of the dots is just the ID field.
right, this is saying that the relationship, each one, like, the first one says less than, the size of the dot determines the effect of relationship on those particular values or those particular heated areas. As you see, each spot on there has a value to it, and they are much bigger than the ones that are individualized by themselves. So
Right, but all this heat map is showing you is that there's more stations in these areas. That's what the
each one of those heat maps, there are only 2 points, and there are points that each one, there are all the points that we are talking about now, so there's no more than that, it's just the value of each one of those points based on the standard deviation and all those other things. That's how you take it based on those factors.
So do you have a question about these?
No, sir, I was just showing you, I was just trying to, what you were getting at before, just trying to find some other relationship with value based on what you said. That's all.
Right. So the reason that these dots get bigger as you go west is because the station IDs get bigger as you go west. This is a station ID. This is the well, it's source ID, not station ID. But this is station ID.
Yeah, I can't explain, I was just doing what you told me. Maybe I told you.
Yeah, this is just this is the density of stations. That's what the map is showing. All right, so let's see. So if we look at particular observations, what we can do is, like, for example, Farmville, Virginia. The actual value is 110.62, but the predicted value was 113. So what happened was that we over-predicted by 3 days. In other words, we said that the late date of the last spring frost was going to be 3 days after it really was. Okay. And so we can use the residuals. So here is the residuals for everything. If we open the attribute table here, we can use these residuals to to come up with. Let's see what the highest residual was. The highest residual was -17. The lowest residual was 14. So, like I said, that's about a 30-point spread. So for anywhere in our area, we could be as much as 30 days. Well, 15 days off in either direction for a 30-point spread. So I guess it's actually 15 days off in either direction. About 15 days off.
So is there a way to show like where it's the most accurate at? I imagine it'd be away from the coastline. You know what I'm saying? Like, so could you just map based on that value and the lowest ones would be the most accurate areas?
Yeah, I mean, you definitely could. You could do that, but to me, these look fairly random. But yeah, mapping the residuals would show you that, and that's something that we would do more in the raster class. But there's a interpo. So if I wanted to make a map, like a continuous surface map, is that what you're saying?
I mean, it could be that or a point, but I was just kind of wondering, like, if
Well,
our
this
model was more accurate, more inland, or if it was more accurate on the coastline, kind of, or is this kind of random?
This map right here is a map of that. So it's pretty random, and we actually ran an autocorrelation test on it, and we found out that it was random. Now we could look and see if there are hotspots, and we could do that by running the high-low clustering on now I don't know which one's which, but it doesn't. I mean, these are all good ones. Input field. We would use the residuals or the standard residuals to do that, and run that guy. Let's just do cluster and outlier analysis, hotspot analysis. Yeah. Okay. Oops, not the right one. Input field residuals. Run that. So I don't know if that makes it any easier to see the cold spots and hot spots. There aren't really. I mean, they're kind of all over the place. They're not in any particular area except for right here, and we kind of already noted that. But it wasn't significant. So we've got some area right around Georgia and South Carolina, maybe even extending over to this point, where we've got some differences that are both highs and lows, a little cluster. I'm not sure what's causing that. To me, it would require some additional study as to why those areas are different than the rest of the pattern. But
Can you change the symbology on what you just did to heat, and you can set some pictures, the symbology, and when you get in the charts, that change it to some symbology. When you right click on it, something there, get well, the hotspot. There.
okay, what do you want me to do?
Okay, now change that to heat at the bottom.
Yeah, so the problem here is that this is measuring sparse versus dense. Like, there's more points up here. It it doesn't really say anything that we needed to say.
Okay.
Like, see, this is just saying that there's more points right here than there are in the other areas. It's like a qualitative measurement. It's just more points in that area. I'm talking about the actual values of the points here, not how many there are.
Right.
We did talk about heat maps and density mapping earlier. Okay, so the size of the residuals matters. Their direction means that they're underpredicted or overpredicted. We can see in some areas 10 days earlier, 12 days late. We did map them. The standard residuals are in z-scores. In other words, they're how far off they are in standard deviations. So go back to the map. I don't know where the map is. Okay. If we go back to the map here, see how this says negative 2.5 standard deviations? That means it's 2.5 standard deviations below the pattern that was predicted, below the linear relationship that was predicted. Okay, if there is a pattern, that's bad. So you look at you can look at this plot, which is the prediction. In other words, the predicted value by the standard residuals. That should be pretty. Standard all the way across. You want that to look like a shotgun that's everywhere the same. You also want the spatial autocorrelation of the standard of the residuals to be random. All right. We already talked about the significance of the different values. So this is talking about these values here, the coefficients, and these are the p-values related to those coefficients. So if the p-value is close to 0, then what that's saying is that the population coefficient determination is significantly greater than 0. In other words, there is a relationship between that variable and the response or the dependent variable. So if this is very close to 0, it's significant, meaning there is a relationship between latitude and, in our case, the average date of the last spring frost. Even with longitude, there's a significant relationship. With elevation, there's a significant relationship. If this is not significant, in other words, if that is bigger than 0.05, what that's saying is that the population coefficient is not significantly greater than 0. In other words, there's not a relationship between those two values. So the model itself, the y-intercept and the slope can be tested for a significance. That's right here. The intercept right here, that is also significant. And then this is the overall model. In other words, is this adjusted R-square significant? Well, yes, that's this value right here. Okay. All right, now there is a problem. This actually gets back to what Elvis asked earlier. There are cases where you'll see a different relationship existing in a different area. So I don't know how many of you are familiar with lake effect snow, but up in the Great Lakes, and actually there's to a smaller degree like out west, the Great Salt Lake is, because there is a big lake next to a frequently cold continental mass, the lake can actually influence how much snowfall occurs. So if we look at the relationship between the distance from Lake Erie and snowfall, we get a pattern that looks like this. I just said, as you get closer to the lake, you should see more snowfall. But what actually happens is as you get very close to the lake, very, very close to the lake, the snowfall drops back off just because there's wind and there's the fact that the snow itself, it takes a little while to form. And so right next to the lake, you don't get a lot of snowfall. Well, you get a fair bit, but not as much as you do just about 10 miles away from the lake is where the peak snowfall occurs, and then it goes back down. Well, how would you model this as a spatial relationship? Maybe this is what you were talking about, Elvis, where maybe you would want to say, okay, well, the relationship right here looks like this, and the relationship right here looks like this. Well,
You start your study area at the 10-mile mark then? Like,
yes.
Once you get 10 miles away?
Yeah, that's one solution, is to cut out that portion of the area that doesn't fit in the model, and then calculate your regression model. By the way, this standardized error, this SE, we didn't talk about that yet, but that's actually a number that represents the spread. Okay, like in other words, let's look at it for our data. Where does it go? Standard error.
As I was clicking each one has a standardized error, divided for each one.
Right. Yep. Each one should have a standard error, and the standard error is like the furthest out that it gets.
We have different standardized error. You got one for intercept, one for elevation, one for the cars to the coast. So if you click on the point, it gives you each error rate for each particular thing you're doing.
Right. Yep. So each of these standard errors is the variance associated with the latitude, the longitude, and the elevation. And this is the overall error. And so if you take the square root of that, you'll get a pretty good idea of what the average error around the line is. All right, so here is here in this case the if we go beyond 20 miles from Lake Erie, we can predict the amount of snowfall that will occur. All right, so there's a couple of steps, and I've tried to basically follow these steps through, but I'm going to go over these slides in case I forgot everything. But when we go to specify a regression model, these are the steps that we want to follow. Okay. First, we want to identify what we want to analyze. Second, we identify potential explanatory variables, and we did that with the last day of frost. I actually went through and calculated elevation and distance to coast manually. How do you think I did that? Like, how would I calculate elevation for those points?
Based on what the actual thing make the calculation from you.
Well, yeah.
Have we done living atlas data in this class yet? I talked about what that is. Have I mentioned that you guys all have access to this living atlas data? Okay, good. So here, just really quickly, I can say I've got terrain data, and I can get an elevation data set for the world. Wonder if there's one that's better just for the United States. Okay, well, I don't need to spend a lot of time. I'll just elevation and then add.
The drop down menu on add data, it's on the elevation source.
There is one there.
Elevation.
Elevation source.
I don't know.
Well, that, yeah, I mean, that's just filtering out elevation data. Like, basically what that does is say, okay, I'm going to add this as an elevation layer. I'm going to add this terrain data in, see what happens. Yep, this will work. So here's all the elevation for the United States, actually for the world. And I could change the color scheme here for the elevation data set. Still doesn't look good. Stretch type. I thought there was a new one, but let's do new class. So this is elevation, and I'm going to make my minimum be 0. I shouldn't have done that. So this is the new one, dynamic range adjustment. What that does is it calculates what you're looking at, and every time you change, it changes the elevation. I mean, it changes the stretch. So anyway, it did a pretty good job here, right? So now we can see the elevation differences that are there. If I want to pull off the individual elevation values for here and put them in my points, there's a tool called extract or something like that. Extract raster. I forget what it's called. Thought I had the word extract in it. Yeah, extract values to points. That's what it's called. So I can take my input features and my terrain data set and then extract the values out. So when I run this, what it does is it goes to the elevation data set and attempts, well, it doesn't attempt, it does, get the elevation value at each of those points. So that's how I can calculate that value. That's the tool that that was used to do that. Now, distance to coast would be a little bit less straightforward, but still it only involved like maybe 2 steps. Well, it depends on what data I can get. So let's look at that. So here is the data that I just extracted. And you see now I have a field that's the raster value. Now the elevation is scaled differently. I think this is in feet and that's in meters or something. It's not quite that, but it's also a different data source. All right, so that's the elevation. How would I get the distance to coast? We've actually done it in this class. Let's say I had a linear data set that represented the coast. What tool could I use that we've talked about in this class? I don't know if we've ever run it yet. That would get me.
I'm trying to think. It was one of those network analysis ones? One of those like...
Not network analysis.
Okay.
Because we're not really working with a network.
True.
But it's the distance from one feature to the distance in another feature layer. It was on the test. Let's see. I'm going to go back here.
the, the memes and stuff like that. I don't remember which one.
Somebody created this, called
So now I've got the United States here, U.S. generalized, and I'm going to dissolve all of the U.S. states into a single feature. So I've got a single feature that represents all of the United States. Then what I'm going to do, I've got all the United States dissolved into a single feature, and I'm going to convert a polygon to polyline. See if it'll do that. Polygon to line. Got my I got my dissolved United States boundary, and now I've got just the coastline. See how I did that? It's not a polygon anymore. It's just a line. I can delete the this one now and this one. So I've got just that line. All right. So now I'm going to run the tool that I was alluding to, and it's called the near tool. So I run my near tool, and I could say my input features, which are going to get the value of the near. That's going to be the one I just made. The near features are going to be calculated the distance from. That's going to be the this one. Yep. And then I don't need a search radius. I'll just say okay. And now my table, I get the distance to coasts. Obviously, it's scaled differently, but it's actually pretty similar. In fact, I could symbolize on this data set now. That's this one. So, graduated colors, and choose the near distance. All right, so you see how I've calculated the distance from the coast using those. See how these are lighter than these? They're further away from the coast. So that's how I created those values in GIS. So identified potential explanatory variables, and I might have had to do, and I did have to do some operation to acquire those. GIS operation. So now the next step is to actually run the regression analysis. We ran the regression analysis using ordinary least squares regression. We could also do exploratory regression, which it really tells you very similar things. I usually run ordinary least squares regression.
And that's exploratory for your regression when you don't necessarily have a dependent variable? Like you're trying to find one given factors, like given other variables?
Well, it's exploratory when you don't know necessarily which factors should be the independent variables, the x variables. With exploratory regression, you still need to have the y variable. You choose that. See, we'll just go ahead and show that. So you still need your dependent variable, and then you can choose your candidate independent variables. So what happens here is, you choose your candidate explanatory variables. And what it does, exploratory regression does, is it runs all of the different possibilities. So if you select 5 different independent variables, it runs it with just each one individually, and then with just the 2. And it shows you the top ones that, it shows you the top values that aren't really, they don't have problems with spatial autocorrelation and things like that. So we could just run this on latitude, longitude, elevation, distance of coast. and then run this guy. Whoop, we still have to say that, run it.
When you work all together with all those different variables, it makes each one of those places unique so that it shows you the way or what it is when you run all three or four work that one particular data. So if you're using a measurement of how large the size is, it's showing you just the
It ran it multiple times. See, the choice 1 of 4 had latitude, distance to coast, and elevation in it. Okay. Then the choice 2 of 4 summary had latitude, longitude. Oh no, sorry. Choice 1 of 4. So if you're only going to choose one of the 4, it's going to choose latitude, distance, coast, and elevation in that order. If you're choosing 2 of 4, latitude and longitude were actually the best 2 variables to choose. Then latitude and distance to coast, finally latitude and elevation. If you're going to choose 3 of the 4, then it's saying latitude, longitude, and elevation are the best. Then latitude, elevation, and distance to coast, and so on. And then it shows you which models pass the criteria of not having a lot of VIF, and the residuals didn't make patterns. So latitude, longitude, and elevation, and latitude, elevation, and distance to coast both passed. But notice that, as we discovered, distance to coast and longitude in the same model didn't pass. It wasn't a valid model. It wasn't a good one to choose. So this runs all of the different combinations. So sometimes I think that running explanatory regression first would be good, but then it'd be better to go in and get the detailed report for the one that you want after running the explanatory regression tool.
Topic or maybe, but like like you have your dependent variables, and we are trying to explain why, correct?
Yeah, you're trying to.
But what if you are trying to find a dependent variable? Like you don't know exactly where it is, or like how cold it is, or something like that. Like you're just trying to take these different variables and find something.
Right. So yeah. So mathematically, like if I was to do that as a statistical tool, what I would do is there are ways to just say, okay, well, here's all my variables, and I want to look at what's called a correlation. So you can have all your variables, however many variables you have, all your other variables in the same variables in one chart and another, and you could actually have all of the correlation coefficients between all of your variables. You could say, this is really high, this is really related to this variable, and that variable is really related to this variable. But you still have to be kind of like trying to find something. Like, you see what I'm saying?
Yeah.
You could explore your data and see what's related to what else, but that doesn't show you a whole lot other than, oh, these variables are related. You still have to take another step. All right. So these are the 6 statistical checks that you need to do. Okay. So first, and we tried to do this as we went through. First, you look at the coefficients for each variable. You see the asterisk next to the probability, and that shows you if it's statistically significant. In other words, is it something that is influencing your variable? So that's looking at the probability number. So that's that number right here. So the first thing to do is to look at these numbers and see if they're statistically significant for your data. Okay. You can also look at the K statistic down here that indicates that the model has non-stationary relationships. Okay, that is given in here somewhere. Yeah, there it is. When that is statistically significant, the relationships modeled are not consistent. In other words, both of these are bad. Stationarity or heteroscedasticity. They mean that your residuals aren't there's a pattern to your residuals, or your data doesn't appear to be normal. Okay, so that's that one right here. So when that is significant, then they're not consistent. So in other words, here's that statistic, and it appears that that is significant, or is not significant. When it is significant, that's the problem. So that's good. That's not significant, so we're okay. All right, the next one is we could examine the coefficient of each sign to see whether it actually makes sense. In other words, here we look at these numbers and we say, as latitude increases, then what that means is that the spring day frost also increases. The days to the last spring frost. That makes sense. As we get higher in latitude, it's a longer time till our spring frost. Okay? Let's look at longitude. It's the negative relationship. So in other words, as longitude increases, in the case where we are, as you go further west, the average date of the last spring frost actually goes down. So we have the thing going down. And again, I don't see why that should happen, but it does happen in our area. Okay. Right? In this case, with elevation, what we're saying is very slight changes in elevation do, in fact, significantly explain some of the variance in the date of the last spring frost. In other words, as you go up in elevation, whatever slight that is, you go up in elevation, you'll see longer times till the last spring frost, and that makes sense, right? As you get higher, generally it's colder. You'll have a later spring frost. Next one is that you need to ensure that none of the explanatory variables are explaining similar aspects of the dependent variable. So this is what we were talking about with the VIF factor. So you want your VIF factors to be under 7.5. If they aren't, you need to throw out one of the ones that aren't. The mathematical term for this is multi-collinearity. What it does is it basically means that you're overfitting your model. You're providing two variables that are basically confirming the same pattern that exists in the data, and you're basically making your model unreliable because it's overfitting the model. And if you try to make it portable into another area, it will be less significant. All right. The next test that ESRI suggests is that you look at the residuals. Now, I just kind of looked at our residuals, and you want them to be spread out. So I was kind of taking a qualitative approach. Yeah, the residuals look spread out. That's these guys. Right? So there is a test to say whether or not your residuals don't have a pattern to them, and that is the Jacques-Barra statistic. Okay, if that test is significant, then the model is biased. In other words, when you see that there's a pattern here that doesn't look right, this statistic right here will be significant, but that's not significant. See that? In fact, that's really insignificant, 0.85. So we're okay on both of these. Basically, you want neither of these to be statistically significant. Neither of those last two. One.
Close to zero.
What's that?
And that means closer to zero.
No.
You're looking at
Now, closer to zero means they're significant. You want them not to be significant, these two.
okay, yes, you want them further away from zero.
Right. They'll have a little star by them if they're significant. And again, these are going to not be significant. When you look at the residuals and you see a pattern that looks like this, they're not going to be significant. They're going to be significant, like if you saw a pattern that showed, like, let's say there was a lot of variability and then very little variability as you got higher, then those would show up as being significant. And then finally, you'll see a warning that states that you should examine the autocorrelation. That's what we did. You want your residuals not to be spatially autocorrelated. If they are spatially autocorrelated, there's two solutions. One is to figure out what lurking variable is causing that spatial autocorrelation and include that. I personally think that's the best solution. So if it's latitude or distance to coast or whatever, you find out what it is, and you can make a better compelling argument about it. The second solution is to do geographic weighted regression, which we talked about earlier. But that's harder to defend because it's making a separate regression equation all along the study area. Now I left this one out. The last check is that you look at the R-squared. We kind of talked about that first. The R-squared value describes much of the dependent variable as explained by the explanatory variables. And that helps us to know if the model's any good. So better models have higher numbers. Now, I didn't talk about this in the lecture, but the GHY number, or the AIC, is another measure of models' performance. The AIC is only comparable for models analyzing the same dependent variable. So in other words, if you run it with average days to last frost free and then you run it again, you'll see the AIC change, okay? If the AIC decreases, when you add more variables to the model, then you have a better model. If it doesn't increase, you don't have a better model. So if we go back over here, you can see how they show the AIC. See, the AIC is 509 here, and it went down to 504 when we added more variables. So that's good. Here, it went back up when we used all four. See how that's 507? Well, that's not good. This is 508. It did technically go down from that one. So that model right there is a better model, or sorry, this model is a better model than that one, but it's not a better model than this one, is what it's saying. Is that latitude, longitude, elevation, distance to coast is a worse model than just latitude, longitude, and elevation. Because the AIC didn't go down. That looks like it was the best model, even though it's almost the same as latitude, elevation, and distance to coast. All right. I think that will go in there. We already discussed geographic weighted regression, and basically its weakness can basically boil down to the fact that you could be overfitting your data by just saying, okay, well, let ArcGIS or let the computer handle how we're gonna quantify and include location into this model.
And you said that was used to fix, step 5, like if the spatial correlation is high?
Yes.
That's what you, that second step?
Yeah, that'll fix it, because what's happening there is that it's including location in the model, and it's basically coming up with a different model in different areas.
Then you said that that's the better way to fix it is to just find that into their.
Yes, well, you'll be able to explain it and defend it better if you can do that. Okay. But let's say you're dealing with just some huge big data question, like you have all of the weather stations throughout the world, okay, and you have all of the data, and everywhere you want to just come up with a way to easily predict the average date to last spring frost everywhere. And you have all the weather stations, and you throw in your data. You shouldn't throw in any geographic data, but you throw in all of the other data that you have, like distance to coast and everything. You just throw it all into the big equation. What it's going to do is if you use geographic weighted regression, it's going to come up with a different predictive value everywhere. And then you can use that to predict values, and again, probably on a big data scale everywhere. So anywhere the user clicks, you could use that, you could rerun that model and come up with a value. But it would be very similar as to if you decided, oh, I'm just going to individually run this just on this little area right here and figure out the value, and then go over here and run it again just over here. But it's for handling a big set of data. You don't want it to handle just 100 points. It needs to be at least 200, 300, 400 points, because what it's doing is subsetting your data and only applying the regression equation for that small area. In fact, I think it would be helpful to, if you go look at the geographic weighted regression help here. It's a regression model, just like any other model. We kind of said population and income might equal crime, but what it does is it says, okay, well, in this area we've got this relationship, and in this area we've got a different relationship. I was hoping there would be other explanations of that. There might be a button. Sometimes there's a button that says learn more about how geographic weighted regression works. I think this is what I was saying. Yep. Still doesn't have. I mean, that'd be a good thing to read through, but that's not necessarily the focus of what we talked about today. Geographic weighted regression was the last slide. It's kind of a newer technique, and it is for big data sets. If we're just trying to explore the relationships, it doesn't tell us a lot of those same things that just ordinary least squares regression tells us, because it doesn't give us one formula or one model for our data. It gives us a bunch of models, and we can't really know what the value was in every location.
So pretty much it makes a new model for each area where the geographic stuff differs.
Yes. It evaluates a local model for the variables you process. So everywhere where you define a neighborhood, what it does is, we defined our neighborhood, we did that little golden selection criteria, and so it decided that using a neighborhood of the nearest 30 points, what it did was it took everywhere you wanted to predict a value, it would look at the nearest 30 points and come up with a regression equation just for those 30 points, and then move on and do that for every possible location. And there was a different regression equation at every 30 locations. And so implicitly, it used things like latitude and longitude to make those predictions, because it was looking through, it was only looking at the neighbors. All right. Why don't we go ahead? Are there any other questions? Why don't we go ahead and stop, take a break here. Let's come back in 15 minutes, so that'll be 25.